Welcome to ExplainerCast, episode 19. I'm your host, Dave Smith.
And this is Shane Swenson.
Today's episode is about high-performance car driving, automotive racing / high-speed driving. We don't know what to title this one.
We'll figure it out.
Yeah.
I pitched this as, let's talk about how to be quick in a car, how to get around a track quickly. Though all these same principles apply in daily driving, we try not to push the limits of the car on the road. But here in Utah, when it's wintry and you've got some fresh snow and ice on the road, you might actually be driving right near the limit of what the car can do in those conditions. And it may not feel fast, but all the same principles apply. So maybe it's performance driving, where performance is dictated as much by the conditions as anything else. On a racetrack, the conditions hopefully let you go pretty fast, but on an icy on-ramp, even slow can be sketchy.
Okay, so maybe it's how to drive at the limit.
Ooh, there you go. I think that's really what it is. Take it to
the limit can move.
Absolutely.
There are many factors besides you and your car that affect the limit.
Exactly, yeah. Okay. So you told me...
Where do we start?
Yeah, you told me that you had done some go-kart racing recently, so tell me how that went.
Well, I've done a little bit of go-kart racing, just a few times, and recently, yes, both electric go-kart on an indoor track that was made of rubber, and also gas-powered go-karts on an outdoor track made of some kind of pavement.
Yep.
Well, I'll tell you, I did a little study beforehand, so I kind of understood some of the principles, but I just couldn't make that darn thing go fast.
Yeah.
You know, it's like, I noticed that one mistake, like, for example, if you let the tires spin out a little bit,
Yep.
or if you approach a corner just wrong, just kills your speed. Like I can feel my speed just dropping like a rock.
Right.
And then rebuilding speed, especially on the gas-powered go-karts, rebuilding speed takes a really long stretch of road.
Yep.
So that's what I noticed. I was very bad at it. Also, when I tried to do things that I thought were right, other drivers would T-bone me. That was another thing I learned.
So tell me a little more about that situation.
Well, like I remember there was one particular corner. So you've got a tight 180-degree turn. So you're doing like a full turn and then going the opposite direction.
Yep.
And so I would approach this kind of wide so that I could start, like let's say it's a left-hand turn. I remember I would kind of approach it on the far right and then do a nice smooth arc and then hug the corner and then end up again on the far right. And when I did that, someone who decided to take the corner very tight just absolutely T-boned me, sending me flying into the other railing.
Yes.
They were thinking, here's my chance.
That's right. Well, and actually you bring up a good point, which is, and we'll probably get into this, there is a difference between the fastest route around the track, what's often called the racing line or the driving line, which what you were doing was to try to make the radius of the corner as large as possible. But there can be a difference between that line and what's called a defensive line in a head-to-head race where you don't want to be passed. Because what you did in that case is you kind of left the door open for someone to come up on the inside. And now, if they had been able to cleanly pass you, that would have been better. When I used to play racing head-to-head video games with my friends a long time ago, we refer to that as the cornering buddy maneuver, where you bounce off somebody else to make the corner because the game would let you get away with it. In reality, it's a little hard on both cars. But yeah, there are a ton of techniques, and we can talk about some of the physics and car dynamics that allow you to be efficient and fast around the track. And then what you were looking at there was even, what's the best line if you're by yourself versus even, well, how do I prevent this person from passing me? And that's more of a racecraft situation.
Oh, I'm so excited about this. This is going to be very, very interesting. And just a disclaimer, we reserve the right to stretch this into two parts. So we depending on how long we go today.
Yeah. Exactly. We'll see where this takes us and if there's more left for next time. So maybe we should take it down to some very basic principles to start with. And we kind of take this for granted when we drive conventional vehicles, but there are some interesting things going on. And so as you're thinking about let's talk about driving by yourself. So you're not worrying about defending against other cars passing you. What were some of the things going through your mind for how to be as fast as possible around that race course?
Well, one thing I noticed was that at the starting line, there was a really long straightaway, and I noticed the top speed of my cart was actually really high, like way higher than I could ever get to through all the other corners throughout the rest of the racetrack.
Yep.
So that was one thing I noticed. The other thing I noticed was it was very easy for the tires to slip. So if I went around a corner at too high of a speed or or if I was riding the brakes wrong,
Yep.
I could slide a lot.
Right.
And in that case, I just felt like, oh man, I'm going so much slower now because building up speed took so long.
Right. Exactly. So yeah, so you're talking about a couple of the fundamental properties here. One of them, of course, is how much power do you have? So how much acceleration can you impart to the vehicle? And then typically, unless you have very high power to weight ratio, you're going to want to preserve that speed, that momentum as much as possible. And so the really crucial factor then is how much grip you have in the tires in order to move the car around corners and preserve that speed. And so if we were talking only about straight line drag racing, then it's really how much power can you generate in your power source and how efficiently can you transfer that to the track through your tires. You're not really worried about turning. Here in the US, oval racing is super popular. And so in that case, it's really how much momentum can you carry through a series of usually banked, gentle left-hand corners. And then the type of driving you were likely doing is what is often called like circuit racing or sometimes road racing, where you probably had a series of turns, both left and right, different size, different radius, different angles. And so it's a more complex mechanism to get the car through the track, and you have to preserve your momentum through the whole sequence. So to break it down to very basic principles, typically, if we really want to look at the limiting factors for this type of driving, it all comes down to the interaction between the car through its tires and the surface that you're driving on. So typically, you're not, in most racing programs, you're not allowed to, say, fly, like be like an airplane and just get above the ground. You're not allowed to use aerodynamics to turn the vehicle. You can use aerodynamics to either make the car maybe a little less heavy on the road, but more typically you'll use aerodynamics to push the car down onto the road to increase the normal force, the downward force that the car is making to the road, which will increase the grip of the tires. And so really the primary limiting factor tends to be that interface of the tires. And so the way I model it in my head is you've got a car, you have a chassis, it's got 4 tires, one on each corner. And when we look at how those tires interact with the road, they're designed to be grippy, but they're grippy up to a limit. And so when we talk about the amount of grip we have, we're looking at friction. And there are 2 types of, in the very general terms, there are 2 types of friction. There's what's called static friction, where the 2 surfaces are not sliding relative to each other. And then kinetic friction, where the 2 surfaces that are interacting are sliding. And most materials have more grip, or what's called a higher coefficient of friction, when they're static, when they're not sliding. And when they start sliding, it goes down. And tires are the same way. So as you talked about, you felt like you lost speed once you started sliding. And that's typical. So ideally, as you make a turn, you would enable those tires that want to roll forward. As you make the turn, there's a lateral force on those tires perpendicular to the direction of motion. And you'd like that lateral force to go right up to the limit of the grip of the tire, but not much past it. A rubber tire, often when it starts to slip a little bit, will still maintain a very high coefficient of friction. But once you start sliding more than a little bit, then essentially it drops down and it feels more slippery, which means less acceleration, less direction changing acceleration. So less centripetal acceleration going around the corner, which means you're going slower, you're coming out of the corner more slowly. And again, on an icy road, a snowy road, even sometimes a wet, rainy road, you might experience this as well, where, again, like I'm picturing an on-ramp that I take to work in the winter. As I start to turn on that on-ramp, it starts to feel kind of slippery, and that means there's less friction that day. And if you start sliding on ice, you tend to find out how little friction there is very quickly.
Yeah. Yeah.
So if it were that simple, then the goal would be to simply take the turn at the speed that enables you to to essentially traverse the corner as quickly as possible. But also your goal is to carry as much speed through the corner because usually following the corner is a straightaway, and you'd like to have as much speed as possible down that straightaway. And so part of the goal here is to maximize the use of the tire, but also to choose a line through the corner that enables you to carry as much speed as possible. So if the track were exactly the width of the car, then it would just have to follow the exact track. You wouldn't have a line choice. But when the track is wider than the car, now you have some choices. And you mentioned that. You said, well, I could take a tight inside line where I hug the inside of the turn. You could also take a very broad outside line where you sort of hug the outside of the track. And if you did that, you would be going around a larger radius, which does enable you, for the same amount of centripetal acceleration, to carry more speed. So with the same grip, a larger radius or a wider turn can be taken faster.
Is there like a trade-off there between the distance traveled and the speed at which you travel it?
Yes, there is. Absolutely. And so if you are grip limited, then typically you want to take the widest radius line possible. And we actually haven't talked about exactly what that curve looks like yet. If you have enough grip, then for the speed that you're going at the end of the straightaway when you get to the corner, then you would want to take the tightest line that doesn't require you to slow down if you have such a choice, because now you'll just travel less distance. And so this is where lighter weight, lower power cars, for example, there's a racing series built around Miatas, and they're very lightweight. They're very efficient in turns, but they don't have a lot of power. And so often, so their goal is to kind of preserve speed, but they also have like go-kart level kind of grip. And so they'll often take, first they'll choose the line that maximizes their ability to carry speed through the corner. But if they have a choice among a set of those lines, they'll choose the one that is the shortest distance, kind of as a secondary optimization, just to get around it faster.
Okay.
So the classic corner to think about, so a 180 is actually a little bit of a weird example. The classic corner to think about is like a 90-degree corner. So picture kind of like a 90-degree, let's make it a left turn, and let's say that the inside, has a certain radius and the outside, is much larger. So you have a few vehicle widths between the inside and the outside to choose from across the track. And again, you could hug the inside. And there are times in a race when you might do that, like if you're defending against someone trying to pass you. You could follow the outside, but this often isn't going to be the fastest line. And in fact, there is a way to plot a larger radius, a less sharp curve through this by starting at the outside of the track as you approach the corner, then turning toward the inside of the corner and reaching what's called the apex of the corner, where you would actually brush up against the inner side of the track, sort of at mid-corner, and then you would allow the car to continue to drift back out to the outside at the end of the corner. So you do an outside to inside to outside. And the radius of that curve is larger than the radius of the inner for sure. It's also larger than the radius of the outer line in this particular example, if you look at the geometry.
Oh, interesting. Yeah, that kind of makes sense. You've created this new circle.
Yep. That's kind of living between the other two. And because it's not a full circle, like if it's a full 180, in fact, then the radius is going to be the same as the outer radius.
Yeah.
You just won't have gone as far, as deep into the corner.
Right.
Anything less than a 180, though, this actually opens up the radius a certain amount.
Okay.
And so because that's a wider segment of a circle, you can carry more speed through it. It also tends to be a safer line than the outside hugging line, because if you mess up, you're probably going to mess up as you try to make the end of the turn, and you're starting more on the inner part of the track and you'll drift towards the outer part. And so you might be able to just wait and not accelerate as much, or maybe even slow the car down a little bit, like if you just came in too fast and it's not working. And so it kind of gives you an opportunity to correct. So that works for a single corner. Things get more complex if you have a series of corners kind of stacked one after another. And typically the way you trace a line through a series of corners is you start with the last one and you say, where do I want to end up with the most speed exiting the last corner? Because chances are you're heading down a straightaway next. And the more speed you carried on that straightaway, you gain the benefit of that speed for the entire duration of the straightaway. So there's like an integral or multiplier factor for that. And so you say, okay, I want to exit the last corner at full speed on the outside. And then that means I need to set up for that last corner for that outside, inside, outside maneuver. And so the one prior to it, I may actually have to, like, let's say it's an S. So I'm going to make a left followed by a quick right. I may actually bias that first left where I end more on the inside of the track because that's on the left side, because that's going to set me up for an outside to outside on the right-hander that's following it. And you'll sacrifice the earlier corner for the later one because the later one feeds into the straightaway. And there's kind of an intuition you build up for this as you look at a sequence of corners. You can also write software that discovers these optimal lines on a track.
Yeah, because I can imagine it's not obvious in your mind, right? Like the trade-off between speed and total distance traveled and the maximum speed you can carry without slipping and the pressure that the different radii impose on the car, right? Like, I mean, there's a lot of factors here. Kind of makes sense that you would brute force that with a simulation.
Right, exactly. And I think, experienced drivers develop some intuition over time, and they start to see kind of the way that the car is going to flow through a series of sections of a track, and they kind of build up that intuition. And you'll hear them argue about it too, like, oh, I do it this way, oh, you do it that way, and then they drive, either check their telemetry and lap times, or do have one follow the other through the sequence and see who's faster. You start to learn that way too. So line selection is important. And I think we all kind of, I don't know if you do this, like when I'm driving like down one of the canyons from the mountains, you kind of naturally trim, I'll say, the corners a little bit. If the road's winding, you kind of start at the outside, you make your way to the inside, maybe you cross the center line a little bit, at the apex. So I think we do this in daily driving as well, if we're not in traffic, if we're not facing other vehicles. And that's just a highly refined process in racing driving. But it's, to me, not the most interesting part of trying to be quick. And to me, what's more interesting is, okay, once you know what line you want to follow, how do you follow that line as fast as you can? And this is where the physics comes in. So the thing I think that makes this the sort of the obvious but yet maybe not obvious thing that makes this interesting is the car is interfacing to the road through the tires. So the car is sitting on the road being pulled down onto the road by gravity. And essentially your only ability to accelerate, brake, or change direction is through the interaction of those tires with the road surface. And your car is necessarily sitting up above that. Your center of mass of the vehicle is some distance above the road surface. And so any acceleration, like when you press on the gas pedal, you feel it press you back in your seat. If you were to look at a vehicle from the side, when they step on the gas, what do you see that vehicle do in addition to, of course, moving forward?
It kind of bucks upward, like the front raises and the back lowers. Yeah,
you see it kind of pitch back. And the reason for that is, again, the acceleration is occurring at the road surface, but the center of mass of the vehicle is up above that surface. And so when you accelerate, imagine pushing on the tires, the center of mass of the vehicle is following Newton's laws. It's resisting that change in motion. And so there has to be a force that's applied up through the vehicle to that center of mass, and it creates a torque. So you're like pushing the bottom of the car forward, but the top of the car is resisting that, and so it kind of leans back.
Yeah, because there's some flex between the wheels and the body of the car.
Yes.
Right,
yeah,
in the form of a suspension.
Exactly. We see, the tires squish a little bit, but really it's the suspension that you see where the body kind of leans back. And then if you stomp on the brakes, you're going to see the opposite.
The opposite.
Yeah, the car is going to kind of pitch forward. And similarly, if you put it into a left turn, the car is going to feel like it's leaning out to the right. And you would see that from an outside observer perspective. And if you put into a right turn, the car is going to lean to the left. So you've got some body movement taking place. What's also happening in association with that movement of the body of the car or its torque relative to the road surface is if you were to look at how much pressure or how much weight each of the 4 tires is carrying and transmitting to the road surface. Like if you had a scale underneath each of the 4 tires, or if you had a pressure sensor like in each of the 4 suspension points, when you accelerate, you would actually see that the normal force, the amount of the car's weight, has shifted to the back. And so the back tires have more normal force, the fronts have less. When you hit the brakes, it's the opposite. You have way more normal force in the front, you have less in the back. And when you turn, the normal force goes to the outside. An extreme version of this, if you've seen like drag racers, they'll sometimes actually pick up the front wheels when they accelerate, or like a motorcycle, because they have such high power to weight ratio. When they really hit the throttle, they might lift the front wheel up entirely because of how much weight transfer has come back. So all the weight of the vehicle's on the rear wheel or rear wheels at that point. And if you were able to generate enough grip in a turn, you might be able to lift up the inside wheels essentially. So there's a tremendous amount of weight transfer taking place. And what's important about that is that weight transfer means there's also a transfer of grip, because the amount of grip you have is the coefficient of friction times the normal force on that interface. So,
right.
Extreme example, you pick up the front tires, there's no grip. If you accelerate a drag racer or something, no grip up the front. But it may be another example, if you really press hard on the brakes, you might have 70%, say, of the vehicle's weight being borne by the front tires, leaving 30% being borne by the rear tires. And that in fact means that you can generate 70% of the total braking force in the front and 30% of the total braking force in the rear. So you could have more than twice as much braking force being generated by your front tires relative to your rear tires.
And what happens when you lean the car into a turn and decelerate at the same time?
Yeah.
Are you now putting some crazy percentage on the one tire?
Exactly. So let's say we're making that left turn, and so let's say you're going down the front straightaway, and it's going to be a left turn at the end of the front straightaway. So you're going at a high speed, and you can't make the turn at that speed. You don't have enough grip to just turn the wheel and go. So you press the brakes as you enter what's called the braking zone, leading up to the turn-in point where you're going to turn in for that corner. That puts all that weight up in the front of the car. If you're still decelerating hard on the brakes and you start trying to turn the car, you'll now be pushing the weight of the car, out onto just, majority onto that, say, front right wheel if you're turning left while under braking. And the question is, can that tire support all of that workload? And the answer is maybe.
Yeah, depending on the speed, right?
Yeah.
And the radius.
And so an example of where this matters in real life is, again, go back to that icy on-ramp. One way that drivers think about their vehicles, they sort of say, well, I only have a certain amount of grip and I have to choose how I'm using that. And if I'm using some of it to slow down, then the amount of grip I'm using to slow down is not available for turning. And if I want to turn at maximum sort of angular rate of change, then I can't be doing any braking or accelerating while I make that turn. If I want to brake with maximum efficiency, I can't be turning while I'm braking. And so the on-ramp is actually a tricky situation, because if I want to slow down but also continue to turn with the on-ramp, you kind of have to balance how much can I be slowing the vehicle versus how much can I be turning it. Because if I'm doing both, I might overwhelm my total grip budget as you're going around that corner.
Well, what are the units for measuring grip? Is there such a thing?
That's a good question.
Is it like newtons or pounds of force that it can withstand in the lateral direction or something like that?
So a common way I've seen grip measured is actually in G forces. So how many Gs, and in most passenger vehicles, it's less than 1 G. So less than 1 gravitational acceleration in a lateral direction. So either accelerating, braking, or turning. And usually you can achieve the maximum G-force either by braking or by turning, because you're probably power limited for acceleration. And braking and turning are both recruiting all 4 of your wheels, where most vehicles accelerate using only 2 of their wheels, so they really have a lot less grip available to them for acceleration, unless it's an all-wheel drive vehicle. So conventional passenger car on conventional tires, maybe you max out it on dry pavement at, I'm just guessing, a number like 0.7 Gs or something like that. A high performance road car with really good tires, like a sports car, you might get up into the 0.8, 0.9 range. And then race cars can do over 1.0. To get much over 1.0, often where you're accelerating laterally as much as gravity would accelerate you downward, to go beyond that, you usually have to have aerodynamic help, where you've got maybe some wings or some other pieces of the body of the car using the airflow over the car to push the car down onto the pavement, increasing that normal force, which then increases the G forces that you can achieve in say a turn.
Okay, cool.
So now we've got a racing line that we've defined as, if we had just perfect control of the car, this would be the fastest way around the track. And it's going to be the one that maximizes the radius, or maximizes the radius of the turns, while giving us the most speed on the long straights, while also minimizing the distance traveled, kind of in that order.
Mm-hmm.
And then now we've talked about your grip budget, and that's really defined by the tires, the car's suspension, and the surface that you're driving on. A very grippy concrete pavement surface is going to have more grip than, again, something like ice or snow or something wet. And then this third factor that we started talking about is that you can move, and whether you choose to or not, the weight of the vehicle will move around to the different tires in response to the inputs of the driver. As you accelerate, moves the weight back. As you decelerate forward, as you turn to the side. And this is where the design of the vehicle comes in, because otherwise you could say, well, if I have two cars at the same weight, the same center of mass, height above the ground, and I give them the same tires, shouldn't they perform the same?
Yeah.
And the next factor is going to actually be how the suspension of the car responds to changes in acceleration. So in my minivan, when I hit the brakes, the weight of the vehicle really leans forward on those front tires.
Yeah.
There's sort of a lot of body roll because it's meant to be a soft riding vehicle. It's got a high center of mass.
It's not a Formula One minivan, right? I'm pretty sure.
Not this one. It's a shame. It'd be fun if it were.
Okay.
Though I did take it out to the track last month for some
nice.
some parade laps at lunchtime with the whole family in it. It was quite fun. But no, not a racing van. On the other hand, a car that's designed a more sports car, or maybe even to a race car, is going to typically have a stiffer suspension, so that the car doesn't move around the body of the car doesn't move, and the weight doesn't move around as much as you accelerate and decelerate and so forth. It's also going to have a lower center of mass, so that torque, when you apply a direction change, whether it's gas, brakes, or turning, there's a shorter lever arm or a shorter moment of inertia, so it's not going to want to lean as much. Like if you could put the center of mass all the way down on the road surface, then
there would be no leaning.
There would be no leaning, right? You'd actually be able to keep the same grip on all four tires all the time, I think.
Tell me more about how the suspension affects the transfer, because I was thinking to myself, okay, if you had no suspension at all, just like rigid,
rock solid
wheels,
yeah,
wouldn't you still feel the effect of the torque on the outer wheels, or on the the affected wheels?
Yeah, you would. So you're right. I suspect that, as I'm thinking through this in real time, the magnitude of that torque is going to be a function mainly of the height of the center of mass. So that the moment, essentially, of inertia from the pavement up to that center of mass. So,
and yet, even having said that, we all know the feeling of a sloppy car that leans really far left and right when you turn, and pitches forward and back when you brake and accelerate, and that seems to have a pronounced effect on the grip.
So the torque, the amount the car wants to lean, if you will, I think is going to be a function of the height of that center of mass above the surface. But the stiffness of the vehicle, the compliance of the vehicle, is going to dictate the degree to which it actually can lean. So I think you'll get a weight transfer that is based on, maybe in proportion to that torque, that height of the center of mass. But whether the vehicle is actually changing the angle of the body relative to the road and kind of sloshing around is going to be a function of how compliant the suspension is, how much movement the shocks are willing to accommodate, and essentially how stiff the springs are that are holding the car in place. And if it's perfectly rigid, it's still going to want to lean a lot, but it's not going to be able to sort of bend or flex very much, even if you have a high center of mass.
Does the lack of bending or flexing affect the amount of normal force that is applied to the tires?
I think on a secondary term it would, because as the body of the vehicle leans in a certain direction, it's actually also translating the center of mass in that direction a little bit. So picture like a big heavy mass sitting above the wheels. If that mass is held exactly where it is, you're going to apply a certain amount of torque to the outside wheels. But if that mass can actually move in response to that to the outside, it's now bringing its center as also moving to the outside, not just the torque. So I think it would.
Okay, got it.
But also, in allowing that flex to happen, it's going to change the time that it takes for a new equilibrium to be established when you change accelerating. So,
okay. Yes. Oh, that makes a lot of sense.
And so as like you hit the brakes, if the car is very rigid, the weight transfer to the front wheels is going to happen very quickly and you're in a new equilibrium. If the car has got a very soft suspension, it's going to lean forward. There's going to be like a time constant. It's going to take some period of time. And then imagine like going through that S-curve scenario. In the go-kart example, you have a very stiff suspension. And so...
yeah. And a low center of gravity too, I think.
Yeah, and a very low center of gravity. Yeah, you're sitting like almost on the ground, and you and the motor are the heaviest things, and they're both quite low. And so as you turn, like you'll feel yourself like pushed against like the side of the seat, but you probably don't feel like the car is like leaning over very much.
No, I didn't feel any of that.
Yeah, and they also have a very wide platform.
I was kind of convinced there was no suspension at all. It felt like
it's probably just the tires and the flex of the frame, honestly.
Yeah,
and you're on a smooth track. So you don't need, like, you're not absorbing bumps or something like that. And so the result is, if you were to do like a back and forth weave, like turn left, turn right very quickly, you would feel the car could kind of reach each of those equilibrium points in the turn very quickly. And so you could slalom, at a high frequency, like back and forth. But picture a very soft, a 1970s like Chevy Impala or Cadillac or something. And now imagine that like weaving down the interstate. You turn left, the car like leans way to the right. It takes 3 seconds to get there. You start turning the other way and the car just leans the other way. And so you can't change what you're doing nearly as quickly. So as a driver... So
what's the effect on grip while the car is in transit from leaning one way to leaning the other?
Yeah, I think while that's happening, you would see the normal forces are rebalancing from their old state to the new state. And so until the new equilibrium is achieved, you sort of have to kind of almost like ease into it and like let it get there. Because if you were going to make a turn at like maximum grip, if you sort of initiate you sort of turn too sharp, and then as the car like leans out and starts to put its full weight on those outside tires, you'll feel those outside tires like be overwhelmed and you'll start to slide. Whereas if the weight transfer happens very quickly, the driver can kind of quickly and precisely bring the car right to the limit and hold it there. So I think you have to be more predictive and you have to be more patient with a car that sort of moves around more, especially in changes.
It kind of makes sense. Like when you think about cornering, you want to get to that state where your outer wheels have maximum grip as soon as possible. Because if not, because those inner wheels, they're just not going to be a huge part of the equation, especially when you're transitioning the weight over there. I almost get this mental model of kind of the car entering like a floating state, where the torque is... it's moving the car, but it's almost like when you throw a ball in the air. The ball's floating to its destination. When it arrives at the destination, now you can actually exert momentum or exert inertia or whatever I think momentum is the right term there, on the ball. But while it's between the thrower and the receiver, if you're playing catch, neither party has any influence on the ball, nor does the ball have any influence on either party. And that's probably an extreme example because cars aren't actually leaving the ground and flying around, and for the most part, they're going to maintain grip to some extent on the road the whole time. But I don't know. Is it kind of like a free fall situation where the car's like, it's like, okay, I was leaning hard right, now I'm going to transition to hard left, and while I'm transitioning, I'm actually kind of losing total mass effect on the ground.
Right. Yeah. So it's actually a really good metaphor because that's how I'll say to me, that's how it feels to me if I'm in a transition, like say from a hard, left turn to a hard right turn. So in like a slalom, the in between is kind of uncomfortable. You feel like, all you're doing is going straight ahead at that period of time, and you're kind of waiting for the car to come find that other side and then feel the grip and the lateral acceleration come back. And so a car that makes that transition faster allows you to just to change what you're doing more quickly without that dead space in between, but it also allows you to do it more precisely and kind of find, take it from one limit to the other pretty quickly. And again, with my minivan, I had to be pretty patient as it kind of crosses from one side to the other. And you sort of feel like it's lost opportunity to be proactive with the vehicle in that time. And similarly with the transition, there's a little extra complexity, like in the transition from braking to turning and turning to accelerating. And we'll talk about that because from turn to turn, or from like brake to accelerate, you're fully reversing the direction of that torque. And so you sort of have to transfer the weight of the vehicle from one extreme all the way to the other extreme, maybe passing directly through center where there's literally no acceleration taking place for a little bit there. And the game is always to be accelerating in some direction, whether it's, down a straightaway, around a turn, or I guess decelerating, in the reverse direction to slow the car down.
Right. So negative acceleration.
Yeah. So you get your momentum, but you don't accelerating right then. But when you're entering and exiting turns, you kind of link like the braking zone with turn entry. So now you have the weight of the car forward, and you try to sort of coax the weight from the front of the car out to the side in kind of a smooth transition. And then as you accelerate out of the turn, you're now going to coax the weight of the car from the side out to the back. So you actually can kind of move it around sort of a unit circle of acceleration, if you will, instead of having to pass directly through the center where you're really waiting on it.
Okay. Oh, interesting. And you mentioned that you feel uncomfortable while the car's weight is making this transition either from side to side or front to back. Do you feel like you have less control authority over the car, or is it just like, no, I just need to wait until I can get into this position so I can make my next move?
Yeah, I think it's a little bit of a feeling of ambiguity. It's always a bit of a comfort to feel the grip, and in that in-between state, you're not actually feeling it. And so you kind of hope it's there. And I guess for me, speaking as very much an amateur, I hope I've made the right inputs so that it's going to work out. And I'm not, especially like say in a side-to-side type of slalom turn, if you bring the weight of the car from side to side too quickly, faster than the car can support it, that is an easy way to put a car into a spin, where you're going to slide and lose directional control of the vehicle. It can be a dicey, it can be a bit of an insecure moment. And again, maybe people that have more practice are like, no, that's not a thing. You just do it and it's going to work. But at least for me, it's like, here we go. Like, I hope that side of the car works too. And I hope that part of the track is good. And then once it's there and it's like holding you and you're like, oh, okay, this is working. Now I know, am I going too fast? Am I going too slow? Is the radius of the turn going to work out? And then you can start to make adjustments with, okay, if I was conservative and I could have been carrying more speed, well, can I accelerate sooner and use the grip that way? Or if I was too aggressive and it doesn't seem like the corner's going to work, then, is there a way to slow the car down a little bit in a safe way, and still make the corner? You kind of don't know that until you're feeling what the car's doing, in the turn.
Fascinating.
Okay, one more thing. And then I think we'll have at least put all the pieces on the table. The other interesting thing is the way we turn our cars is a little bit weird because we steer with the front wheels and the back wheels sort of have to follow along. And if you were to trace a perfect curve, you would actually want to turn your front wheels like toward the inside of the turn, and the back wheels maybe outside, turn them out a little bit, like if they were all going to trace the curve perfectly. But we don't do that. So we actually end up needing the tires to slide a little bit as you go around a turn. And
just the rear tires?
Yeah, the rears all potentially. But yeah, so like the rears, because they just want to go the direction the car is facing, you end up, you're kind of dragging them, the front tires are kind of dragging them around the turn. And so, but that's not the most efficient way. You really do want to slide the rear tires a little bit to make up for the fact that they don't point outwards as you go around the turn. And so there's a property that's very important for vehicles, which is the balance of grip between the front and the rear tires. And a car that has more grip in the rear tires relative to the front is one where if you try to turn the car more sharply than it can handle for the given speed, the front tires will lose grip and the car will sort of plow sort of straight or turn less than you wanted. And so that's called understeer. And that means you were limited by the front grip. And most passenger cars are designed by default to understeer because it's kind of the safest thing to happen if you're going to run out of grip. And my minivan definitely understeers, as I learned on the track. The other extreme is as you pull the car into a turn, let's say you have lots of front grip and you don't have enough rear grip. Now the rear tires are going to start to slide outward. The car is going to rotate toward the center of the turn faster than you wanted it to. That's called oversteer. The car is rotating more than you want it to. And again, the fastest way around the corner, if you're grip limited, is a little bit of oversteer because it's helping those rear tires come around the turn. But too much oversteer turns into a loss of directional control and a spin. And so not great for passenger cars. Lots of fun if you're into drifting and you sort of like to go sideways. And so there's an aspect of car design and setup to try to balance those properties. And then there's a lot of driver control associated with balancing those in real time as well. As far as the car setup side goes, most passenger cars have front wheel drive. And so your front wheels are responsible for accelerating and turning. And that just tends to bias them towards understeer. And the rear tires are kind of along for the ride. Many race cars are rear wheel drive. So your acceleration is in the rear wheels, and actually you can do some engine braking in the rear wheels as well. So you can actually put both positive and negative torque into the rear wheels via the gas pedal, and then the front tires are for steering. And then of course some vehicles are all-wheel drive. So as you're going around this corner now as a driver, you have some input into whether the car is going to oversteer or understeer. And as an extreme, when I was a kid, I don't do this as much anymore, but when I was a teenager and I grew up on snowy roads, a way to for sure achieve oversteer was to pull the handbrake mid-corner and lock up the rear wheels.
Oh, yeah.
And, around you'll go. And so
it's great fun.
It is.
I don't actually own a car that can do it anymore, but man, that was fun times.
Yeah, it's a lot harder if your parking brake is like a foot pedal or something. But yeah, that's one way. If you have a rear wheel drive car and it has enough power, you can do what's called a power oversteer, where you just give it enough gas and you can now overcome the rear grip with acceleration. And that's what that's what drifting is. Mm-hmm. You can also induce oversteer in a rear wheel drive car or actually on any car, you can induce some oversteer if you apply a little bit of judicious braking as you try to turn. And the reason for that is as you hit the brakes, you're pushing some of the weight of the car forward. You're reducing the normal force on the rear wheels. They have less total grip. You're actually adding some grip to the front wheels. And so a little braking can increase the grip in the front wheels available to you, decrease the rear grip, and allow you to now enter the turn with a little bit of oversteer. If you do too much, you might spin the car. And so another way you can do that also is on a manual transmission. If you lift throttle, and so you're essentially allowing the engine braking to kind of decelerate the car, but it's only decelerating the rear wheels, you'll now have transferred some weight forward, and you'll have applied that negative acceleration, that deceleration torque to the rear wheels. And again, they might break loose. And so you can do this on purpose. It's also the thing that makes driving a rear wheel drive car in ice and snow or slippery conditions pretty tricky, because
especially when it's a rear wheel drive car that has very little weight in the back.
Exactly, like a pickup truck. If you haven't put some ballast back there, if you hit the gas too hard, you might lose traction in the back. If you even decelerate, just lift aggressively, thinking, oh, I'm going too fast, I want to try to slow down quickly, that can also cause you to lose rear grip and then send you into a loss of control, a spin or something like that.
Interesting. Yeah. Okay.
So now as you're driving the line, as you're managing grip, then the next thing you're doing as a racing driver is you come into the braking zone, you're slowing down as much as the car is capable. So you usually try to get right to grip limited, like just before like your ABS, your automatic braking system, would kick in. And sometimes called threshold braking, because you're right at the limit or threshold of your grip. And then if you just sort of let off on the accelerator and turn in, you're probably going to spin. So you actually kind of need to let off the brakes. You can just gently let off brakes as you ease the car into the turn, so that you can smoothly take the car from decelerating to turning. You're going to move the weight of the car from the front wheels out to the outside wheels of that turn. And again, you want to do this in proportion to how quickly the car's body or its chassis will move the weight to those tires, and do it in a way that you're balancing the front and rear grip, you're balancing the oversteer versus understeer tendencies of the car. That all happens at turn-in time. Now you come into that corner from the outside to the inside, come close to the apex, and often as you are hitting the apex, you've been at neutral throttle, so neither accelerating nor decelerating, and you begin to apply more throttle, with the goal being to be at full throttle by the time, if not before, the car is straightened out and pointed down the next straightaway. And again, as you do this, as you add some throttle, you're going to induce some understeer, where the front end of the car is getting less weight, so it's going to have less front grip. It's going to kind of push out to the side of the track. If you have a high power vehicle and you just stomp on it, you probably, again, induce a spin, power oversteer. But somewhere in between is the sweet spot, where you've maximized the speed around the corner, you've maximized the exit speed around the corner as well. Again, by smoothly moving that grip from the front of the car in the braking zone to the side through the turn, and then out to the back of the car as you accelerate away. And then just repeat.
That's amazing. Tell me about, maybe we need to pause here and go to part 2, but I'm very interested to understand the smoothness factor here. Like, why does that matter? It's not more like a binary input on the brake and the gas. Why does the curve of the amount of gas you add and brake you add make such a big difference?
So, the smooth part is really, I think, about the fact that the vehicle can't instantaneously change from one regime to another. And so you need to, as a driver, ideally you go at about the same, you change the inputs at the same rate of change that the car can accommodate that change. And so again, if all the weight is on the front of the car and you're in the braking zone and it's this big, slow to change car, and you just hit the gas super quickly, you'll provide a bunch of torque to the rear tires before there's actually weight back there to keep them pressed to the ground, and you'll spin them. And similarly in turns and so forth. Now in a go-kart, you can actually be pretty quick, because the go-kart can switch from fully grip limited turning in one direction to fully grip limited turning in the other direction very quickly. And like a Formula One car is also they have an extremely fast time constant. But a passenger car, the extreme case like my minivan, you have to be pretty patient with it, because if you try to change what it's doing faster than the actual sort of, I think the normal forces can move, then you won't have the grip to accommodate what you're trying to get the car to do in terms of accelerating, decelerating, or turning available in the tires that it needs to be in. The other thing just is extra inputs or wasted inputs. So every time you turn the wheel, You're putting a little bit of friction between the front and the rear wheels. They're pointing in different directions. There's a little sliding and slowing down. Anytime you're braking more than you needed to, or you're not accelerating as much as possible, or even trying to accelerate in a turn versus going straight, those all slow the car down. So trying to find the minimum set of inputs that gets you around the track, and those that are timed to the ability of the vehicle to accommodate the change, is I think where the slow comes in. Because if you watch a Formula One driver's hands, they're not slow, but compared to maybe for their brains, maybe that is slow. But you watch someone driving more like a sports car, even a racing driver, like they're gonna be, they're not moving their hands as fast as a Formula One driver, because their car can't accommodate a change of input as quickly and still maintain that right at the limit performance. And maybe that's the other thing is, if you're truly right at the limit and you ask the car to do more than it can do in that particular dimension, you're going to start sliding, and that will slow it down. And so now you're trying to coax it from, fully grip limited braking to fully grip limited turning to fully grip limited acceleration without ever crossing the limit, because that's going to make you slower, but also without leaving too much margin between what you're doing and what the limit would be, because that's opportunity that's left behind. And so tracing that line takes finesse.
Do some cars come equipped with sensors and metrics you can look at to say how close you are to the grip limit?
I don't know if cars do. You can certainly put, like, racing teams will put telemetry systems on their vehicles, and so they're measuring acceleration in every direction. And so I think those systems can quickly build a model of, okay, today on the track, here is the envelope of grip. Here's the maximum sustained acceleration I've seen in any direction. And then you can have a real-time display of what's the current lateral acceleration of the car in any direction relative to that performance envelope. And then as a driver, you can try and sort of keep the pip out on the edge of that envelope, which tells you you're at least doing the most that can be done. Now, you still have to have a good line. You still have to be doing other things right, but at least you're using the vehicle.
Right. That's so interesting, because I have as I try to imagine what it would take to develop an intuition for using your own body's own senses to know how close you are to the edge of that envelope of performance where you're about to break out of the grip, but still taking advantage of as much of it as you can. That's just like, wow, what an interesting, that must take so much time to develop that intuition, because you think about, you got to feel how much the car is lurching one direction or the other, nosediving or pitching up, leaning left, leaning right, understand your speed, understand the radius. And the only way you've got it wrong is if you overdo it, because the car, breaks grip and slides. And there's no way to know, it seems like, how close you are to that edge, other than just lots and lots of experience.
I think with experience, and this is true in so many domains, with experience, you learn how to intuit like second and third order and beyond factors. So again, the model we've talked about where there's like static and there's sliding, there's actually a whole bunch of in between where you're kind of just sliding a little bit. There's a whole science. They talk about slip angle, which is like how much is the tire sliding versus the direct, going forward. And it actually turns out rubber tires generate maximum grip at a non-zero slip angle. So they actually are sliding a little bit, just not a lot. Like they haven't fully switched into the sliding friction regime. And so if you're if you take a turn too slowly or you're not braking hard enough, you can feel it because there's sort of like, there's no dynamic to it. And if you fully overdo it, of course, but at least even for me, and I think it's probably more so for more experienced drivers, when you're right at the limit, there are a number of clues there. You can kind of feel a little texture from the tires moving across the track a little bit. You can feel it through the steering wheel for the front wheels. You can feel it through the seat and kind of your body as well. Some street tires will actually make a lot of sound and tell you when you're at their grip limit. Racing tires tend to be pretty quiet. But also, like if you turn a little bit too much on the front wheel, you'll actually feel that the force that it's trying to straighten with, the restoring force, diminishes as you enter understeer. And so you kind of like tune for like maximum feedback, force feedback, if you will. and you can kind of feel the rear, like is the rear starting to like sort of step out and slide more than the front or less. And so I think drivers do develop this intuition of their grip budget as well through cues like that. Again, I don't want to, I feel that in my driving, and I see a lot of drivers that are a lot faster than me, so I assume they're all the more in tune with those factors as they progressed.
Very, very interesting. All right, what more explaining do we have to do here, Shane?
Yeah, we might have just about done it. I was going to make one more kind of reduction to reality for people listening to this and wondering, well, if I don't take my car to the track, like how do I experience these things? And so obviously in a car, you want to be very thoughtful about ever pushing limits. Personally, I kind of like a snowy parking lot as a chance to at least notice what it feels like when the brakes lock up and the car doesn't want to turn anymore. Because if your front wheels aren't rotating, they can't turn you because they're just sliding now. The other place you can feel at least what braking up to the limit feels like is on a bike. Again, be careful. Don't get hucked off your bike. But if you try to stop with only the rear tire, only the rear brake, you can't stop as fast because the weight is transferring forward. I don't recommend stopping only with the front brake. You might go over the handlebars, but you can also kind of feel, how to use both brakes. You find you use the front more than the rear. You find that there's that sweet spot where you're not sliding, but you're still using most of the grip. That's exactly what's happening in a car as well. So I find that's another place you can kind of practice these techniques.
Awesome. All right. Well, we had some explaining to do. We did the explaining. Have we explained all we need to explain?
I think we did.
This was very interesting for me, Shane. I love it. It was, I don't know. There's so much more. There are so many more dynamics at play driving around than I realized. And next time I get on that go-kart track, I can't wait to just absolutely dominate with everything I've learned today.
Sounds great, Dave. All right. Well, thanks as always.